So I hope at this point everybody knows how to get the live stream, and I don't have to share it with all of you. So welcome to our 10th lecture. I have this is my third class from the morning. So if I make any silly mistakes, please don't mind. All right. So last time I started talking. So we have talked about Lorentz transformations and this invariance of space-time intervals. And then last time I started talking about we've talked about these hyperbolic rotations and all. And last time I started talking about these space-time diagrams and how these space-time diagrams are really nice in helping us to understand what happens when we look at different observers in different frames of reference. So in the previous class, for instance, I used this space-time diagram to show you how the relativity of how simultaneity is a relative concept. That means you have two observers, one is O and one is O prime. According to O, there are two lamps, and these two lamps emit light, and that event, that emission of light, is simultaneous as seen by O. And by simultaneous, we mean that it happens at the same time. So at a constant time, so those events happen on a constant time slice as seen by O. But when we go to a new frame of reference, we have some observer O prime who's standing on the platform, and this is a train and it's moving with some speed v naught. Then with respect to O prime, right, what happens? With respect to O prime, if we draw the time axis of O, it looks like this diagonal line over here. And similarly, if we draw the space axis of O, it looks like this other diagonal line. And what is this diagonal line? What is the slope of this line? The slope of this line is 1 by beta, right? So, sorry, the slope of this line is, what is it? It's the opposite, I should. So, yeah, this will be 1 by beta actually. Fix that. And this will be 1 by beta, and the slope of this line, the x-axis is beta. Now I can see that the 2 points which were at the same time according to O prime, they are no longer at the same, they don't happen at the same time, because this is O prime's time axis, right? And if I ask what is the time at which this event happens at this time over here. And similarly, this event happens at what time? It happens at this time, which is a different time. Okay, and now we can calculate how much that difference is by using this Lorentz transformation. Right? Okay, so I had asked you to do this exercise. Did anybody try this exercise? Can you raise your hands in the Zoom window if you tried this exercise? Do you know how to use the raise hand option in Zoom? Yes, no? Well, nobody's raising their hand. Raise your hand if you know how to use the raise hand option in Zoom. That will tell me that you know how to use the raise hand option. So many people have raised their hands, but many people have not raised their hands. So maybe if you don't know how to use the raise hand option, please look it up. If you have a desktop, then it's easy. But if you are on a mobile, it might not be so easy. But you have to find it somewhere in the interface. Okay. But please look it up. This is a very important thing for communication. Okay. All right. You can lower you can stop. I will lower everybody's hands. All right. So yeah, you can lower your hands. No need to raise hands. Now let me ask you, did anybody try this exercise? Can you raise your hand if you tried this exercise? Okay. All right. So since we know that most of you know how to use the raise hand option, and since I don't see a single raised hand, that means almost none of you actually tried this exercise. That's okay, because well, it was just yesterday, right? But the point of these exercises is to do them on a day-by-day basis. All right. Okay. So so this is a basic property of Lorentz transformation. This quantity, which is called the space-time interval, remains a constant bit for any two events. Okay. So today we'll continue talking about these space-time diagrams and space-time intervals. Lecture 10. Okay. So before I go on, are there any questions? Okay. All right. So let us look at this delta S squared once again. So we have two events in space-time. Okay. One event has these coordinates and other has these coordinates. Okay. And we calculate the space-time interval, which is c delta t squared plus delta. Okay. Now, if you just look at the spatial interval, right? So remember that our space-time is four-dimensional, right? So we should actually be using four coordinates: x, y, z, and t. Right? But for simplicity, we generally, when we're talking about relativity initially, we throw away two of the coordinates. But if you want the full picture, you have to use four coordinates, right? So in this case, what is delta S squared? It's minus c squared delta t squared, right? Plus delta x squared delta y squared delta z squared, right? Now, this has two parts. One is the spatial part, which I can write as delta r squared. Okay. What is this delta r squared? This is just the distance between these two spatial points, right? This is a single spatial point, this is another spatial point, and this is the distance squared between those 2 points, right? Now, what is the property of this delta r? Delta r, this distance, it is always greater than or equal to 0, right? It is always greater than 0, and if delta r is equal to 0, that means the points, the 2 points, they coincide. That means they are the same point. So the spatial distance between any two spatial points is always positive, right? And the only time the distance is 0 is when the points are on top of each other. But now you look at this delta s squared. Delta s squared can be greater than 0, right? If delta r squared is greater than c delta t squared, right? If this part is greater than this part, right? So these are squares. That means they are both positive numbers. This is a positive number and this is a positive number, right? So you're taking the difference between two positive numbers. It can be equal to 0, which means delta r is equal to c delta t, than 0, which means delta r is less than c delta t. Okay. Now, what is the meaning of these three possibilities? Let's look at the 0 option first. Let's look at when delta s squared is equal to 0. When does this happen? Right? We can see that it happens when delta r's magnitude square is equal to c delta t, right? Squared. Or in other words, if I take delta r by delta t and I take the magnitude, I get c. Okay. So that means, so if I draw my space-time diagram, I have my space coordinate and my time coordinate. And now I have some 2 points, okay, A and B, right? And what am I doing? I'm calculating the distance between these 2 points, right? And this distance is 0, right? That's the interesting thing. Points don't coincide, but the distance between them is 0. Why is that? Why is it 0? Because when I look at delta r is what? Delta r is the spatial part. So what will that be? That will be this part, right? Delta r will be and what is delta is the temporal separation between the 2 points, right? And delta r by delta t is equal to the speed of light. It's equal to c, right? Yes. So for a second, you can just forget about the y and z coordinates. Fine. Just think of delta s squared in this delta t squared plus delta x squared. And let's just say this is equal to 0. If this is 0, that means delta x by delta t is equal to c, right? What does this mean? What does this tell us about the line which connects these 2 points? right? There's a line which is connecting the 2 points, right? So if this is the relationship, then what does this tell us about the line?
The slope of line is 1, sir.
And so that line would correspond to what physically,
Has the speed equal to light.
right? So that line corresponds to something that is moving at the speed of light, right? So this is something which is moving at the speed of light. We can just think of it as light. So this is something which is moving at the speed of light. Okay. So any 2 points in separated such, if I release a beam of light at A, a flash of light at A, that flash of light will reach the point B. Okay. Delta S squared. Let me draw you another diagram and illustrate this slightly differently. This is X and CT. Okay. Now I'll draw my diagonal lines, right? My 45-degree lines. What do these lines represent? What is any line? Any line in the space-time diagram represents some object that is moving, right?
Yes, sir.
It's moving in space-time. So even if I have a straight line like this also represents an object in motion, right? It is moving in time. It's not moving in space, but time keeps changing, right? So if you stay sitting in the same position for your whole life, you will get older, right?
Yes, sir.
So your personal clock, your personal time clock will keep moving, right? So what do these lines represent? These 45-degree lines?
Objects moving with speed of light, sir.
Okay. Somebody other than Venu Madhav next time.
So,
okay.
so the video on YouTube's audio is not clear, sir. It is stopping in between.
I don't know. I can do nothing about that, right? I mean, all I can do is I can start the streaming. I have no control over YouTube and over your network connection. And if you are asking this question on Zoom, then I don't know why you need to worry about YouTube. I didn't understand that part. Like, are you already on Zoom?
So I'm already on Zoom, but if I don't understand something, I'll just on YouTube. I'll just go back and see that again. So,
Oh, well, you should do that later, no?
yes.
You should do that after the class is over, because if you try to do it during the class, you'll miss what I'm saying now.
Yes.
I-
So I basically watch on YouTube, and if I don't understand something, I will go back and I'll catch up on YouTube itself.
no, bhai, that's fine. Okay. But a better strategy, I mean, in my opinion, is to just watch the Zoom, attend the Zoom sessions. And if you don't understand something, to ask a question in the class.
Okay, sir.
That is my, I think, a better strategy. Whatever your question is, no matter how simple your question is, no matter how silly or how stupid you might think your question is, please ask me. Okay.
Okay, sir.
So then you can always go and watch on YouTube and whatever. So to
Okay, sir.
everybody, this is my request. Please ask me any question that anything you don't understand. And if it is happening, if it is so happens that you are not understanding anything, fine, tell me that you are not understanding anything. But please tell me that. Okay. Now, is there anybody who has not understood anything so far? Can you raise your hand in the Zoom window? Well, people will be reluctant to raise their hands, I suppose, when I ask such a question. So let me just recap the things I have discussed so far, right? We have had 10 lectures. What have I discussed so far? My network is being slow. We've discussed the Newton's laws. We've discussed conservation of momentum, energy, and angular momentum, right? And we have talked about what it means to have the total momentum of a system. We've talked about the work energy relationship and how to derive the work energy relationship, right? How to get the expression for the kinetic energy, right? I've talked about Newton's law of gravitation, right? And from the law of gravitation, how to get the acceleration due to gravity near the surface of the earth, for example. But see, all of these things, they are useful only if you sit down and work through the derivations on your own. If you don't do it, then it doesn't matter whether you sit in class and attend the class, you will not understand. Okay. No matter how simple or how nice my explanations may be, unless you do it yourself, you will never understand. There is no alternative. So it is not too late. If you have not done so as yet, please go to the very first lecture. Start with the first page and watch the YouTube videos and work through each step yourself. This is the only way to understand what is going on. Now I realize that you have many classes to attend to, and it's not possible to, well, it might be asking a lot to do this for every single class. But if you want to understand my subject, physics, then this is what you need to do. Okay. Okay, so we have this picture, these space-time diagrams. When I say that I have 2 points here, okay? A and B. What do we mean? We mean that, well, something is sitting at those 2 points, right? And we define a distance between these 2 points, some delta R magnitude, right? Now, What is a space-time diagram? It's the same thing, only with one extra coordinate. That's it. That coordinate is the time coordinate. But you have to think a little bit differently. Okay. When you think of these points in just spatial terms, when you think of this coordinate here, it is something that stays the same forever, right? It's something that is static. It doesn't change, right? Okay. But if you were to look at the same point in a space-time,
Sir, you're getting stuck.
is it better now?
Voice keeps
Yes, sir.
breaking.
No.
Voice is keeping breaking,
Huh?
and your video is getting stuck, sir.
Yes, sir.
I don't know, man. क्या करूं यार मैं बताओ, है ना? मोदी जी बोले थे कि विकास होगा, पता नहीं इंटरनेट ऐसे ही चल रहा है आजकल, किसको ब्लेम करूं मैं? Right? नहीं, I have taken broadband this thing connection. I've taken Zoom because Zoom is much better and faster than Microsoft Teams and Google Meet. And I'm paying for this Zoom connection myself out of pocket. Other than that, what else can I do? So
So now it's totally fine. You can continue.
yeah, sometimes it takes a little bit of time. So when you look at the same point from the space-time perspective, this point is not a point anymore, right? It becomes a line. So now you have this A and this B. And when I say that, when I look at this picture, I say that this A and B, they exist at the same time, right? This is a snapshot of my system at a constant time, at a single time. How do I represent that in a space-time, this picture? Well, A and B will lie on this line, right? What is this line? This line is all three coordinates, X, Y, Z, all of them clumped into one line, okay? Now I could even draw two space coordinates and one time coordinate. For instance, I could draw this as X and this as Y, and then this as CT. Then, for instance, I have this point A over here and this point B over here, right? And if I think of these 2 points now, what happens? As time goes on, these 2 points keep moving, right? So what is a single point over here? A single point is what we call an event. And what is a line? A line is a collection of events, right? So for instance, you look at a person who is running. There is somebody who is this is not a very good runner stance. I guess that's good. So you look at this person who is running, okay? Right? Now these are the snapshots of that person at different instants of time. So let's say t is equal to 1 second, 0 seconds, 1 second, 2 seconds, and 3 seconds. Right?
Sir, not
Okay.
audible, sir.
Huh?
Voice was clear.
Again, sound problems,
Yes, sir.
voice problems.
Sir, one idea, sir. If you stop the live streaming in YouTube, I think it may come in Zoom.
I don't think I don't think that makes any difference actually. Okay.
Sir, putting off your video can even help sometimes.
I'll try. Venu, you have to turn off your video also, no?
Okay, sir.
Okay. Anna? So each one of these snapshots is an event. Am I audible now?
Yes, sir.
Yes, sir.
And a
Yes, sir.
collection of events, right? A sequence of events is what I called a world line. This is a fancy word for saying it's the trajectory of some particle, right? Now, the thing is that even if you don't have any motion, right? Even if you are just sitting in place, meditating, what happens? The world around you keeps changing, right? Just because you sit and meditate doesn't mean that the world comes to a stop, right? So other things keep happening, right? For instance, the sun will rise, right? And it will set. Right? If you keep a watch, if there is a watch sitting next to you, the watch is also, the time is going to keep ticking in that watch, right? That watch will not stop ticking just because you are meditating in one place, right? So if I ask what is the position of this observer, right? The spatial position is the same, right? X, Y, and Z are constant. But what is the time coordinate? The time coordinate is not a constant, right? Is there any disturbance now?
No, sir.
It's clear,
Okay.
sir.
So if you look at this observer in this space-time diagram, what do you see? You see this observer moving along a word line, right? This is how you specify the motion of this observer. And each of these points is an event, right? Each of these times is an event. Now, what if you have an observer who is moving, okay? So there is some observer who is moving. What does this observer see? Does this observer see you at rest? No, right? This will say that, well, you are here, and at one instant of time, that the other instant of time you are here, and then at the next instant of time you are here. Okay. Audio problems? Okay.
So this position of this meditating bus is in frame of reference of the runner, right?
Right, exactly. So in the frame of reference of this observer, this meditating person is no longer at rest, right? So if you look at this same observer in the frame of reference of the moving of the runner. Okay, so now I will draw the runner's space-time diagram. This is x prime and ct prime. These are the coordinates of the runner. So the runner is O prime and this guy is O. So according to the runner, what is happening? How will I describe the position of this chap? Well, I will say that at one instant of time, he is here, he or she, right? Then at the next instant of time over here, the next instant of time over here, the next, okay, oops, the next instant of time over here, right? Right, has a trajectory. This is the trajectory of the observer as seen by the runner, O prime. Fine. Is this okay? Audio problems again?
No, sir, not problem.
Okay, so that trajectory is the same as this trajectory, right? They are the same trajectory. This trajectory, when I look at it in the runner's frame of reference, it looks like a line at some angle, right?
Sir, why is not passing through origin, sir?
It doesn't matter, right? It doesn't matter because, you know, I mean, it just depends on the origin is a there is no such thing as a fixed origin, right? I can always move my origin around anywhere I want, right? And if I have one line that passes through the origin, that's okay. That is one that represents one moving object. But another moving object will be somewhere else, right? It will not pass through the origin, right?
Okay, sir.
Right?
Sir, why isn't the runner moving vertically with respect to time?
The runner is moving vertically. This is the runner.
Why isn't he moving?
This is the runner, this vertical axis.
Yes, sir.
Right? Any vertical line
Okay.
in this space-time diagram, any line that goes vertically up represents the one runner's world line. Right?
Yes, sir.
How do we get that exact line equation, sir?
That's the point, right? How do you get the line equation? That is where the so let's say that
Sir, audio cut, sir.
this okay. Now
It's okay, sir.
Now let's say the position of this meditating observer, right, in the O frame of reference is X. Okay. And X is a constant. Okay. So this is x is equal to constant. Fine. Now I want to ask, the question is, how do I get this line? What is this line, right? This line is some x prime and some t prime. So I have to use the Lorentz transformation. X prime is equal to x minus v naught t, right, times gamma. T minus v naught x by c square times gamma. Okay. Now, what is happening? This x is a constant, right? So let me just set x is equal to 0. I can take x is equal to 0 for convenience. So I place the meditating observer at the origin in his or her own rest frame. Okay. This is just for convenience. What happens now? V naught t minus V naught gamma t. Audio problem again?
No, sir, it's clear.
And t prime becomes just gamma t, right?
Yes, sir.
X is equal to 0. Now, what is the relationship between x prime and t prime?
T prime is equal to minus V
You
naught
can just
x.
look at it and tell, na? This is equal to minus V naught
V
t
naught.
prime. That is what this line is. That is what this line should be, right? It cannot be anything else. And if I move it from the origin, then I will get some x prime naught. If x is not equal to 0, right? In which case I'll get something like this, right?
Sir.
Shifted from the origin. Line is simply the line of a moving observer. That's it. Yes? No? Anything? So let's go back and look at some of the original diagrams that I had again. Okay. Right. Any vertical line represents an observer at rest in that frame of reference. Okay. So they are at rest. They don't have any velocity with respect to that frame of reference, right? That is a vertical line. If I have any line that is diagonal, so such as this orange line here, this is a diagonal line. What does this represent? There is a displacement in time and in space. So if I look at any 2 points along the line, right, what connects those 2 points It is something that is moving with a velocity, which is given by, what is the relationship between the velocity and the slope of this line? The velocity okay. Now, any line which has slope equal to 1 corresponds to something moving at the speed of light. Any line with slope greater than 1 corresponds to something moving at a speed less than light, and vice versa. And line, you don't have to keep that in mind, right? I can have a line anywhere, and so for example here, this is a light bulb that emits a flash of light. Now these lines, these two orange lines, they don't pass through the origin, right? Which is fine, but they represent rays of light because they both have slope equal to 1. Then maybe I will skip it, and we will just not use it. In previous semesters, I have found it to be very useful. But, I suppose every class is different. So if you are all having difficulties, maybe it's because of Zoom. Maybe it's difficult for me to convey this over Zoom. Okay, so all right. Well, let's meet tomorrow, and in tomorrow's class onwards, we won't use the space-time diagram picture anymore, and maybe then you all will feel a little bit more comfortable. I don't know. See, because again, nobody turns their videos on, and if you don't turn your videos on, then I can't see your faces, and if I can't see your faces, then I don't know what is going on in your heads, right? Okay, so I'll stop here. Just try to understand the space-time picture if you can. It's very useful. Anyways, tomorrow we'll come back and we'll derive this length contraction and time dilation. Okay.
Okay, sir. Thank you.
Okay, sir. Thank you, sir.
You're welcome.
Thank
Any
you, sir.
questions?
Sir,
Thank you, sir.
sir, question one thing, like what does CT represent in the y-axis, sir?
So why do I put C? Is that the question?
Yes, CT is the dimension of meters, sir. Like
Meter. So I put C so that it has the same dimensions, right? Okay.
what does that indicate? Not, I don't have the clarity, sir. Like
Well,
what is it CT dash?
So this is the time of this observer. This is the running observer, O prime,
Yes, sir.
right? This running observer has their own clock with them, no?
Yes, sir.
That clock is represented by this CT prime.
Sir, we can also write CT also, no? But like because T prime is equal to
No, because T is not equal to T prime.
Lorentz transformation. Okay.
Lorentz transformation. So if we could do that, we wouldn't need space-time diagrams really.
Sir, like I'm confused, sir, but in the first, I mean, like in the first lectures, we told that T prime is equal to T, like the time is same for
No,
anyone.
I told you that I said that is what we
Galilean transformation.
huh? Right,
That
that's the
is-
Galilean transformation. That was the understanding before relativity, before the special theory of relativity.
Sir, but like for everyone there is a standard time now, sir. Why would, like, I understood this Lorentz transformation, but why
Yeah.
would we be changing?
Well, that I will give you some examples tomorrow. But the first thing is that, look, these two postulates, right? They say something about the nature of our world, right? The first
Yes.
postulate says that the laws of physics are the same for all inertial observers. Okay,
Yes, sir.
that makes sense.
Yes, sir.
That makes sense if you believe in the relativity of motion. Now, all of the laws of physics that we have so far, all of the experiments that have ever been conducted, they all confirm the relativity of motion.
Yeah.
They all say that there is no way to measure your absolute velocity with respect to any frame of reference, fixed frame of reference.
Yes, sir.
Then the second postulate says that the speed of light is the same in all frames of reference.
Yes, sir.
Okay.
Yeah.
So at the time that Einstein invented this theory of relativity, see, it took people a long time to accept this theory. Again, for the same reason that you are saying, right? It took people many decades to accept relativity. Because this goes against our intuition. Our intuition is that there is a fixed time for everybody.
Yes, sir.
Right? I think of somebody else on the other side of the planet, or I think of somebody in the other side of the galaxy. Right? But the fact is that if you assume that the first postulate is true and the second postulate is true, if you assume that the speed of light is the same in all frames of time, okay, then what happens is that when you look at time intervals, right, so this is time dilation, which I will talk about tomorrow, length contraction and time dilation. When you
Sir,
look at
here
time
there's
intervals, for a moving observer, the time interval, just 1 second, please, somebody's ringing the bell, 1 second,
Okay,
sorry.
sir. Yes, sir.
Okay, sorry about that. Somebody was ringing the doorbell. So if you look at time intervals, right? If I look at delta t and delta t prime, they will not be the same. So that is what we'll talk about tomorrow, time dilation. So the whole point of relativity is that time is not the same for everybody. Okay.
Sir, tomorrow you tell me some examples, sir.
Yeah. No, I'll give you examples tomorrow, right?
I'm not understanding perfectly. Like, I am still stuck at the point that time is obviously constant for everyone. Then why is this time dilation coming?
No, because, well, then you haven't been paying attention, because I was very clear that that is the understanding before Einstein.
Yes.
Right? That was the understanding before Einstein. Okay.
So that means if there is a possibility, we can go back in time.
No.
So future?
No. Well, you are going into the future.
Like I can jump into the further future, sir.
No. No, sorry. You can't do that. Relativity is not the same as magic. Okay. Relativity is a different, modifies our understanding of space and time, but it does not suddenly turn the world into something, a magical place where you can time travel and where you have fairies and dragons. The world is simply still very much a physical world,
Yes.
which obeys the laws of physics. You cannot create an infinite amount of energy out of nothing. You cannot destroy energy, you cannot create momentum or destroy momentum. All of these things are preserved. The only thing is that the way we describe this, it changes.
Sir, the last doubt, we have discussed in the few last so many class before experiment, no sir. There we said that only the horizontal thing get contract. Why not the vertical one, sir?
Sorry?
I forgot the reason, sir. That scientist.
Yes.
Right.
Why
Morris
is the
experiment, Mosley
contraction
Morris.
right? Why is the contraction only in the horizontal direction?
Yes,
right?
sir. Yes, sir. I forgot.
Right. So that's a good question to ask. Why should it be that, right? So one explanation. Okay. So see, whenever we come up with some law of physics or some equation, right? Again, it is not a magical process. We don't like get some divine insight. We look at what experiment says. Experiment tells us something, and accordingly we make our equations. Right. So now, what the Michelson-Morley experiment required, right? It required this contraction only in the horizontal direction. Okay, that's the first thing.
Yes, sir.
The second thing is that if you think about it, the sense in which motion, that if there is some kind of contraction, right? If there is some effect of the motion, it should be along the direction in which the motion is. Right? You have a plane that is perpendicular to the motion, right? For any vector, you have a two-dimensional plane that is perpendicular to that vector, right?
Yes, sir.
Now, in that plane, you could have anything that is going on.
Yes, sir.
But all of that will be independent of what happens in this direction, right? If I look at the relative motion between objects, the relative motion along the x direction is independent of the relative motion along the y direction.
Yes, sir.
And independent of the relative motion along the z direction.
Yes, sir.
So if you make this assumption of independence of direction,
Sir, net. Your voice not clear.
independent direction,
Stuck, sir.
then you have to make this. Then you end up with the natural conclusion that the contraction will happen only along the direction of motion, not along orthogonal direction.
Sir, the voice got cut. So still here we could hear that the relative motion is only in x or y or z, and after that everything got broke, sir.
Okay, so relative motion is only in the x, y, or z. So that means you are treating x, y, and z as linearly independent dimensions, right? They are independent dimensions.
Yes, sir.
So if I move in x, if I treat space as a three-dimensional system,
Yes, sir.
right? That means I need three independent parameters for each point,
Yes, sir.
right? So each parameter is independent.
Yes, sir.
So if I take a vector which represents the velocity, then I have a orthogonal plane, a
Yes, sir.
perpendicular plane.
Yes, sir.
Now, whatever happens in this perpendicular plane
Yes.
should not be affected by the relative motion in the orthogonal direction,
Yes, sir.
right?
Yes, sir.
Because if that's the case, then my space is no longer really three-dimensional,
Yes, sir.
right?
Yes.
So now it is possible that maybe at some very high energies, okay, it is possible that this Lorentz transformation has to be modified in some way to take into account the transformation of the orthogonal directions also.
Yes, sir.
So this is the thing, right? Whenever we say that we have some long range of validity, okay. So when I say that the Lorentz transformations of special relativity is the law of physics, it has some range of validity. So it is possible that when you go to very, very high energies and very, very close to the speed of light, special relativity itself might need to be modified. And some sort of change like you are talking about might happen. Okay.
Yes, sir.
But again, we don't have any evidence that that happens.
Yes, sir.
And we have these massive accelerators which are sending protons and electrons at 99.99999% of the speed of light. Right.
Yes.
So if there is such a change, then it will not match with our predictions, right?
Yes, sir.
And then, well, we'll try to come up with something new.
Sir, one more. So now understood, sir. You said that this length contraction only happens in the direction of motion.
Mm-hmm.
So that means the Earth moves in the horizontal. What is it, sir? Why not in the vertical and no contraction in horizontal? That can happen, no, sir.
Sorry.
The length can contract in the perpendicular one and not in the horizontal one, no, sir. Why
No,
particularly?
so the direction of motion of the Earth, right? So I mean, if you look at the Michelson-Morley this diagram, direction.
Sir,
Yeah, okay, it updated. Now
Sir, voice is getting cut.
can you see the figure? Okay, can you see the figure?
I can see the figure, sir.
Okay, so if you look at the Earth in this picture
Yes,
in
sir.
January, the Earth is moving in this direction,
Yes,
right?
yes, sir.
So which arm is in the direction of motion?
Horizontal,
It is the B. It is the B arm.
Yes, sir. Understood, sir.
Okay.
Understood. Yes, sir. Understood.
Okay. All right.
Thanks, sir. Yes, sir.
And any other questions
No, sir.
from anybody else?
Sir, last one, sir. Sir, this wave equation is there, not, sir? E naught into cos of kx minus omega t. So you gave a homework that Galilean transformation is wrong. Because that dou square e by dou x square is 1 by c square into dou. So in that, when we substitute, we should substitute like this, sir. Cos k in x, we should substitute x minus v naught t, and then solve it, sir.
In what? Sorry, how should you substitute? You'll have to show me the solution like this. I don't. It's hard to follow what you're saying. You should write it down and like share it on the group. Okay, share it on Telegram or on Moodle.
Like Galilean transformation was wrong because it was not satisfying this Maxwell's law, no, sir.
Right.
Okay, sir. Yes, I understood, sir. Thanks.
Yeah. No, but if you have like more of a doubt, you please write down the equations and like take a photo or scan it and then share it on the Telegram group, or you can post it on Moodle also.
Yes, sir.
On Moodle, along with questions, you can put photos and pictures also.
Yes, understood, sir. Thanks, sir.
Yeah.
Bye, sir.
Any other questions from anybody other than Ashwin? I mean, assuming Ashwin has asked all his questions. Okay. All right. So I'll stop the recording and the live streaming at this point. Okay.